Hello, so I'm going to explain the MEXT undergraduate physics for 2015. So we go to question 1, number 1. A point particle with mass m is thrown with speed of v at an angle theta above the horizontal axis as shown in figure 1.1. The acceleration due to gravity is denoted as g. Find the distance L to the point where the particle hits the ground. So what you have to know to solve this problem is that you have to know these three common uh, equations for kinematics, and this is in the case of when the v is accelerated by an constant a, so the acceleration is constant. So the first equation is v is equal to the initial velocity plus at, and the distance is just the integral of v in respect to time. So the integral of v naught in respect to time is v naught t, and the integral of at in respect to time is a half times at squared. And for the third equation, to remember this more easily, you can write 2a times the distance is equal to the v final squared minus v initial squared. And you have to know that when there is something that is moving diagonally, uh, you can see it as the horizontal component and the vertical component. So when there is something that is moving at an angle theta, the one that is adjacent, the component that is adjacent to the vector is v cosine theta, and for the one that is opposite of the angle is v sine theta. So to solve the problem is that we see this v just as the two components, that is Vx and Vy, and let's analyze the horizontal component. So when let's just imagine the ball moves like this. You should know that the horizontal component of v is always constant, or you can think that there is no other thing that's affecting the horizontal component of Vx. Like when you think about it, there is no hindrance for Vx to be stopped, so the v is always constant, so there is no acceleration for Vx. And for Vy, you can see like this person here looking towards here, or when you throw the ball, like let's say you throw the ball at like this, the ball, you can see that the ball is moving like this. It's just like throwing the ball up and then it comes down. So you can see the vertical component as that is the same as you throw the ball at the upwards and then it came down. So let's analyze the horizontal component first. Since there is no acceleration, we just can use that the v velocity is just the distance divided by time, and when you write it in the term, when you write it equal to the distance, it became v velocity times t, time. And we know that, so I'll write v naught here is to not confuse the v that is in the kinematic equation. So we know that phi naught in the horizontal component is just phi naught cosine theta times t, and we want to know L. So but we don't have this equation in the answers, so we need to search t. And when you think about it, the t, we know t is by analyzing the vertical component. By the vertical component, we know whether it has done falling or not. So uh, when the ball is at its maximum position, the time the ball takes for it to reach the maximum height is the same time as the time it took for the ball to reach the ground again. So we can see this two phases as the half of the time that it takes from the ball from here to here. So we can solve the time by just looking the first phase, and so we can just solve it by when the ball moves thrown upwards from here to here, and when the ball reaches the maximum height, the v is 0, the velocity is 0, and we want to find the time. So we can see of the three equations which we can use. So let's see h. For the second equation we can't use it because this is for searching for h, and we don't need to search for h, so the second equation can't be used. For the third equation, there is no variable time, so the third equation can't be used. So we use the first equation that has the time component, that has the variable time. So we can write phi in here as 0. So we change the phi naught as phi naught in the y component, that is the phi naught sine theta, and the t component, the t variable, as t over 2, and we can move g t over 2 to here, and we can write this in equal to t, that is 2 phi naught sine theta over g. And using the equation that we had before in analyzing the horizontal component, that is phi naught cosine theta times t is equal to L, we can substitute t from here. So we substitute 2 phi naught sine theta over g to t, we get 2 phi naught squared times sine theta times cosine theta over g. That is the answer B, number 2. So there is a planet with a moon. The moon has an orbital radius of r and a period of t. Assuming the orbit is circular, find the correct formula for the mass of the planet. Here, the gravitational constant is denoted as g. So the theory that you have to know is that omega is 2 pi over t, and you can write it also as v over r. And since this is a moon that orbits a planet, we know that it has a centripetal force. So whenever there is an object moving in a circular motion around something, so around a point, then we know that it has a centripetal force towards the center of the circle. and we can write it as m times the radius of the circle times the omega squared, and we can also write it as m times p squared over r. And since there is talking about a planet, about planets, there is also a gravitational force that is attracting both of the planets to each other, and the gravitational force is the constant g times the mass of times the product of both the mass, so that is m. So we can write the mass of the first one as big M and mass of the other one is small m over the distance squared. So we can write that there is a planet and there is a moon. So let's say the big planet is m, the big M, and the mass of the moon is small m. And when the small moon rotates around the planet, we know that there is a centripetal force. But since this is two planets, we can also write the F centripetal is also the force of the gravitational force between big M and small m. So we can write F centripetal is equal to F gravitational. So for F centripetal, between these two equations, we need to know since the answers there is 4 pi and t, we need to use the equation that has the t. So we need to use mr omega squared for F centripetal, and we can write F gravitational as gmm over r squared, and we can write omega as 2 pi over t squared. 2 squared is 4 p squared over t squared times r, and we can cancel the mass of the moon here. So we are left with r 4 pi squared over t squared is equal to gm over r squared, and we search for the mass of the big planet, so we can write this in equal to m, in equal to big M. So we move g to the bottom here and r squared to the top here. It became 4 pi squared r cubic over gt squared, that is c. Number 3. So an ideal gas is enclosed in a container with volume V and pressure P. The gas expands adiabatically into a vacuum. The volume changes from V to V plus V prime in this process. Find the final pressure. So the theory that you have to know that you have to know it is that PV over T is always constant, and since adiabatically means that the temperature is constant, we can write PV is equal to PV after. So we can write the P after the process is P prime, and the V after the process is just V plus V prime from the problem. So we can move V plus V prime to the bottom of PV, and we can get the answer, that is V over V plus V primes times P, that is A. Number 4. A point particle of mass m and charge q approaches to a point particle of charge q at a fixed position, so they're both positive. When the distance between the two particles is L, the speed of the moving particle is v. The permittivity of the vacuum is denoted as epsilon naught. Find the minimum distance between the two particles. So what you have to know for this problem is that the concentration of mechanical energy, that is the sum of the potential energy and kinetic energy before, is equal to the potential energy plus the kinetic energy after. So the mechanical energy is always conserved. And for this case, we should know that the potential energy of a charge is 1 over 4 pi epsilon naught times uh, the product of both of the charge over r. And for kinetic energy, we know that it is equal to a half mv squared. So from the problem, we know that the charge of small q is moving towards the big Q until it stops, until it's until they repel each other. Since they are both positive, they will repel each other if they get close. So let's say that the minimum distance is d, and d is when the phi is equal to 0. Since the phi moves from here, the phi reduces as it goes. The phi is reduced as it goes towards the big Q. So to express this process, we can use the conservation of mechanical energy to this. So the mechanical energy, or the potential energy of the small q in here, is 1 over 4 pi epsilon naught times big Q times small q over the distance, in this case that is the big L, plus, since there is a kinetic energy, the and a speed of phi, and we know that the mass of the charge small q is m. We can write it as a half times mv squared. It is equal to 1. It is equal to the mechanical energy of when it is at the minimum distance. And we can write the potential energy at the minimum distance as 1 over 4 pi epsilon naught times big Q times small q over d. This because the distance of here is d. Plus, since the phi is nothing when it is at the minimum distance, the phi is 0. So a half times mv squared when phi is 0 is the wall kinetic energy is 0. So we can solve this in terms of equal to d. So to make our life easier, we can remove this a half, so we can multiply all of this by 2. So this times 2, we know that we can cancel. We can divide the 2 big Q small q over 4 pi epsilon naught by 2. So the 2 becomes 1, and the 4 pi epsilon naught divided by 2 is 2 pi epsilon naught. And we can do the same for the right side. And to make our life easier too, we can multiply all of this by 2 pi epsilon naught L. So this times 2 pi epsilon naught L is just q, and mv squared times 2 pi epsilon naught L becomes this, and the right side times 2 pi epsilon naught L, the 2 pi epsilon naught cancels and L stays here, so it is QL over D. And uh, we can move the left side to the bottom so that we can find D. So the answer is QQL over QQ plus 2 pi epsilon naught mv squared L, that is C. Number 5. A light ray travels through two parallel slabs having different indices of refraction n1 and n2 as shown in figure 1.3. Which of the following choices is true regarding the relative size of indices of refraction? So the theory that you have to know is the Snell's law that says the refraction index n1 times the sine of the angle that is normal, that is normal to the horizontal line, is equal to the n2 here times sine beta. So the angle here that is normal to the horizontal line of here. So from this equation we know that the alpha is obviously smaller than b. So because alpha is smaller means that n1 is bigger, since alpha and n1 is inversely proportional, and since b is bigger, n2 is smaller, since they are are inversely proportional. So we can write that the n1 is bigger than n2, and the answer is A.